Hello students, in my today's lecture we're going to talk about force and pressure. So we're going to start with the topic which is familiar to you. In today's lecture we're going to talk about the elastic materials, plastic materials and Hooke's law. So first of all, about elastic materials. So how we can define elastic materials? We can say on bending or on stretching, the material which loses their shape and then they again come back or regains its original shape when force is removed, that is known as a elastic material. So on removal of deforming force, a material regains its original shape and size is known as elastic material. So let's say we have elastic material and the length of the elastic material is the L. So right now the initial length is the L and you're putting the force F to the right. So on applying the force, this material will become something like this. Its diameter will decrease and length will increase on applying the force F. So if you remove this force is known as a deforming force because this force is basically responsible for changing the structure of a body. So it's a deforming force. So if you remove this deforming force, on removal of deforming force, body will again regains its original shape and size. And this is applicable within elastic limit. Within elastic limit. If the force is very high, means beyond the elastic limit, then the body won't regain its original shape and size. For example, the example of elastic material, steel, rubber, etc. So these two are the elastic material. But keep this thing in mind that steel is more elastic than rubber because its elastic limit is very large as compared to the rubber. Coming to the next, plastic material. So for plastic materials, we can say on bending or stretching, they loses their shape. On bending or stretching, they lose or loses their shape. They keep their new shape when the forces are removed. So you can say they keep their new shape when forces are removed. So what are the examples? What are the examples of the plastic material? The example of plastic material is a plastic. You can say plastic, glass, etc. So these are the examples of a plastic material. So this is the difference between elastic and plastic. So in simple way, if the body again regain its original shape and size, the body is elastic. If the body is not gaining its original shape and size after removal of deforming force, that's a plastic body. Coming to the next, let's talk about Hooke's law. Hooke's law. So when you're writing the statement for the Hooke's law, it's very important to specify this Hooke's law is applicable within the elastic limit. So according to Hooke's law, within elastic limit, an applied force is directly proportional to extension. So we can say F is proportional to E. If you remove this proportionality sign, you will get the constant K. And this K is here spring constant. So how we can get the value of spring constant? We can get the value of spring constant by F by E. And one more thing, if you see that the value of K is very large, so it means that particular spring is the hard spring. If the value of this particular K is very low, it means that particular spring is the soft spring. Now let's take one example. So there is a fixed end and the spring is attached to a fixed end. And at the other end, the mass M is attached. So this mass is putting the downward force, that is the mg. Basically that's a weight. Or sometimes the authors are using the word load also. So if you're using weight or load, both is same thing. So if you keep on increasing the load or if you are keep on increasing the weight, you can see there is a change in the extension, and that is within the elastic limit. So here the extension you're going to calculate like this: final length subtracted by the initial length. So take care of this thing, students. There's a initial length is different thing, and extension is different thing, final length is the different thing. Sometimes the student confuses between the final length and extension. Extension is always calculated with the help of difference between final length and initial length. So here when you have to plot a graph between load and extension, and in the next class you are going to conduct this experiment in the lab also. So if you have a different force F, which is in Newton, an extension which is in meters, so the graph would be something like this, linear graph. So in this graph, the gradient of this particular graph, gradient will be del F divided by del E. So that is F divided by E, and F divided by E is a spring constant. It means here the gradient of the graph will give you the value of a spring constant. Now sometimes in the same they ask you to show where is the elastic limit. So how you can identify in particular graph at which point you have a elastic limit. So let's say the graph is like this. This is force, this is extension, this is in, let's say, centimeters, this is in newtons, and our graph is going like this. Now see here, at which particular point the graph is getting non-linear. At this point. After this point, the graph is getting non-linear. So this particular point, this green point, is known as a elastic limit. So this point is the elastic limit. Okay, what is the SI unit of a spring constant, students? What is the SI unit of spring constant? SI unit. So here the force is measured in newtons and extension is measured in meters. So Newton per meter is the SI unit of a spring constant. Right, let's talk about some more cases. In the same, the force extension graph. So let's say this is the force extension graph. And the graph is something like this. Like this. And now this time, this is a force and this is the extension. Now here students, they switch the force and extension. So why I'm drawing this diagram, because you should know that after the elastic limit, we need a less force to change a more length. So that's why you should band like this. If it's like this, which already I discussed with you in the last graph. If it's like this, and this force is in newtons, this x is in centimeters. Now this time this F is on the y-axis and the extension is in centimeter on x-axis. In this case, the graph will go like this. So this is your elastic limit. So see, it's banding along the extension. Here it's bending along the extension. So keep this thing in mind. If they are switching the places, then you have to extend the graph like this along the extension, because at small force F, there would be a more extension after the elastic limit. So this point, this particular point is here. This point is showing the elastic limit. Okay. Now, what is the elastic limit? How we can define elastic limit in the exam? So we can say for elastic limit, elastic limit so this is the load beyond which Hooke's law is not obeyed. Hooke's law is not obeyed. So this is a standard definition of the elastic limit. Or students, you can also write like this, or you can say the load beyond which the spring is left permanently stretched. So that is a elastic limit. Okay, coming to the next about the graph, some more important points. If the graph is like this is the first graph, next this is the second graph, and next this is the third graph. Now here on y-axis I am taking force in newtons, x-axis extension in meter, here force in newton, extension, no, this is not extension, this is the L. L means final length, and this is in meters. In this case, this is the force in newtons, and this is the extension in the meter. Now, in the first case, the graph is like this. Graph is like this. Let me use different color for this to express the graph. The graph is like this. In this case, the graph is like this. In this case, the graph is like this. Now, what are the differences between these three graphs? Is all three graphs are correct? Think about this. Which one is correct? This one is correct, third one, or second one, or first one? So students, here, first graph is not correct. Why? Because see, you're giving the force F and there is a no extension. So according to Hooke's law, this graph is not making sense. As per the Hooke's law, this graph is not correct. Is this graph is correct? Yes, this graph is correct. How come this graph is correct? Because from here to here, this is the initial length of the spring. So this length L is the, or I can say L naught. So L naught is the initial length of the spring. So sometimes they give you the graphs like this and they ask you to figure out the initial length. So initial length of the spring. Okay, in this graph, why I plotted this graph? Because the gradient of this graph won't give you Hooke's law. Because the gradient of graph will be del E by del F. So in this kinds of graph, the spring constant is reciprocal of the gradient. So basically keep this thing in mind always that our K is the del F by del E. So if gradient is not looking like this, then you have to take a reciprocal. If on the y-axis there is a force, on the x-axis there is extension, then the gradient will give you a spring constant. Right. Keep some notes with you. Note number 1 for the IG exam, that rubber, if in the MCQs there is option, Rubber is there, steel is there, plastic is there, and many other. Sometimes they confuses you with the elastic materials only, the examples of elastic material. So rubber does not obey Hooke's law because its elastic limit is very very close. First and second note, between rubber and steel, steel is steel is more elastic than rubber. More elastic than rubber. And why? Something called the Young's modulus, which is not in the syllabus of the IG. The Young's modulus of the steel is greater than the Young's modulus of the rubber. Right. I hope these concepts are clear to you. Let's do some questions on this. So the question is, a spring is stretched 10 millimeters by weight of 2 Newton, and we have to calculate first the spring constant, and second the weight of an object that causes an extension of 80 millimeters. So first solution, it's very easy. Simply they're asking for the spring constant, so you know that for part A, the F is equals to Kx. So K would be is equal to F by X. X is basically extension, or it's better to use the E because throughout I'm using the E. So E and E. So force is 2 Newton and the extension is 10 millimeters. So spring constant is 0.2 Newton per millimeter. Part B, they're asking for the weight. So you can use same thing. F is equal to Ke. This force is basically a load or the weight. So here the value of K is known to us, which is 0.2 Newton per millimeter multiplied by the extension, and extension here is the 80 millimeters. So this is within elastic limit. We are considering that this thing is happening within elastic limit. So this gives you 16 Newton. So when there is a force of 16 Newton, that will cause extension of a 80 millimeters in the spring. I hope this is clear to you. Okay, last topic in this, the combinations of a spring. Combinations of a spring. So students, if we have a spring like this, and if I am putting the force F, what type of energy is getting stored in the spring? Which type of energy is getting stored in the spring? That is known as the elastic potential energy. So about this we'll talk in the force and energy. Right now I'm not discussing about the energies. Okay, so here I have a spring which has a spring constant of K1. I have another spring which has a spring constant of K2. Now there are two possible combinations are there. Basically three are there, but in our IG syllabus there's only two. One is the series combination, one is the parallel combination, and third one is the mixed combination. But mixed combination, I didn't see the questions on mixed combination in IG paper. So first is the series combination. So in the series combination, the springs are connected in series like this. Spring 1 and then spring 2 and then mass. So this spring, this is the mass M, so the weight is acting down. The first spring will show you extension. So first spring will show the extension x1 and second spring will show the extension of x2. And why the extensions are different, student? Because they both have a different spring constant. So in this case, the total extension, would be a x1 plus x2 if the springs are connected in the series combination. If in the question they are saying the spring constants are same, like both has a spring constant of kk, so if spring constant is same, then the extension E would be x plus x, and that would be 2x. So this is in the series combination. Let's see what is the story in the parallel combination. So let's say there's a one spring. Let me make a heading parallel combination here. Parallel combination. This is the second combination. So let's say there's a spring which has a spring constant k and it's showing a extension of x when you're putting the load here. When you're putting the load. Now, if you're connecting a spring from the fixed end, the springs are connected like this and like this. And this is the weight. So this will show you extension of x by 2 and this also show you the extension of x by 2. It means in this combination the extension is only x by 2. Don't take like this x by 2 plus x by 2. No, the change, the vertical change is only x by 2. Keep this thing in mind. So in this, it's a parallel combination. In this combination, extension is equals to x by 2. Okay, might be the one question is coming in your mind that if the extensions are different, then if the spring constants are different, if the value of k1 and k2 is different, then what about these? This time also it would be x by 2, x by 2? No, it won't be x by 2 and x by 2. Then what would be the final extension? That is not a part of IG syllabus. But yeah, later on when you going for engineering and all, there you will learn that if you have a different spring constant, how you can get a net extension. Or if you interested to get to know, so you can write me an email, so I will reply you and give the answers on that. Right, so that's it. So let's conclude the things. First of all, we talked about the elastic and plastic materials. Then next in our lecture we talked about the Hooke's law. Next in our lecture we'll talked about the exam problems, like what kind of question generally the IG asks. And next we discussed about the combination of springs. So in the next class, we're going to do a numericals on the topics which I covered today. Right, student? Take care and have a good day. Bye bye.